This topic, we will be learning how to select the best model. But in this situation, we will be using only the training data, meaning that we are going to be calculating the model selection scores only based on the performance at training phase. Only training, only. But I still confirm that if you can do the validation, in my opinion, it's still better. Usually, this is done when you really cannot afford to do the validation. But sometimes, yes, the more scores you have, the better decision you can make as well. Because sometimes one score can give you multiple answers. That could be the case. Okay. Usually model selection not only is done on the training, but also it encompasses two components inside it. Usually it has the components that reflect the quality of the model. Okay, here exists the model quality. And the model complexity, that is how complicated it is to compute this model. And if you look at this selection score, let's say if we have high loss function, if this one is high, probably this means that your model is not good yet. It still have high loss. And usually this loss is going to be something like RSS, or maybe like a negative log likelihood, which is still an RSS term. And model complexity, of course, if your model is highly complicated, that means it requires high computation and possibly lead to high variance. And therefore, it's probably not an ideal model as well. So the best model should be the one with the low loss and the low model complexity. But usually you wouldn't get both. You usually get one or two. Usually life's like that. But anyway, we will see each of the score. Okay. Let's say if we have a set of model parameter, let's say we have the parameter itself and the function, whether or not it's deep learning, support vector machine. Let's say we combine that function with the model parameters and put it as a set of alpha. And then we also have n to denote the number of parameters, or maybe number of input features. Usually they are equal. And also we have m data point. And m data point here is like the number of samples in your training as well. Okay. So here are the scores. You can have what we call the AICc score. That is a negative of 2 multiplied log likelihood. Actually, this log likelihood is very, very similar. It is very similar to the RSS score. If you derive that right from the beginning, it will look very similar to that. And after that, it's added by 2n. And this 2n is like 2 times the number of parameters. And as you can see here, even though it's right at the negative, okay, I'll just put this way. You can think of this, the entire term as 2 times RSS of alpha. So this means that this score, the higher is the worst one. Actually, the lower is the better. The corrected AICc score has a similar tendency, that is, it has like this negate of log likelihood, this 2 times number of parameters, but it also have this additional term. This additional term actually help compensate when the number of measurements aren't that high. That means if your training samples are small, you better have this term to help compensate when choosing the model. Next is the BIC score. This one, they changed the complexity term into n log m. So pretty much as you can see here, everything is like a variation of each other. Actually, these three, they usually use it together to find the best model, because the tendency between them is like the components between them are very much aligned. Like they are based on the log likelihood of the score and added with some complexity. And for the FPE is slightly different. That is, V alpha here is actually like a correlation between the residual. Sorry, it's like a, it's not, sorry, it's a trace, okay, of the, if you have like y minus y hat. It's a trace of this error. So it's still like an RSS. Again, for this term, if your score is high, it's bad because it's RSS times something. Likely the Mallow CP is an RSS plus something. So up until this Mallows, the lower score, the better. The only thing that the higher the better is still the adjust R square. Actually, it have a very similar concept of having 1 minus RSS over TSS. The only difference is that they have this complexity term multiplied to the error term. So adjust R square would be the only one that the lower, sorry, the higher is the better. Pretty much that's all for this scoring. In details, okay, I will just give you this example. Here they kind of show variations of how you might compute each of this score versus, sorry, they show the result of computing these scores versus like the number of predictors, which is n in our case, that is like the number of parameters in our case. And as you can see, AIC, BIC, AICc are usually shown together because they are based on the same loss function. And another thing that you can notice about is the fact that sometimes, yes, like AICc here, they give you maybe multiple choices. Meanwhile, AICc and BIC maybe give you like a more concrete result. Like, let's say for AICc, they give you this as the best and maybe and this one. Meanwhile, BIC is only this point. So it's like these scores may be used together to reach a conclusion. Because of course, you probably want just one model to represent your case that work the best. You probably don't want to run multiple of them and then it's like each of them give you a result, right? Another thing that is the adjust R square. This one, they kind of plot adjust R square versus R square. And if you remember, R square is the one where you compute only 1 minus RSS over TSS. This means that the line of this R square is representing the change of model performance, just the model performance for each number of predictors. What is suggesting that with this R square, it's telling you that the higher number of predictors is the better, which is kind of like telling you nothing, because in training phase, everything here is computing training phase. Of course, in training, what you would see is that the higher number of complexity parameters, everything will give you the better result anyway. But if you compute the adjust R square, and as you can see here, actually these points is the best for them, not a whole way through. Like for R square, it's going to be these two. Like the adjust R square will give you like a decision that you compensate with your model complexity, not just the training loss, because the training loss will always improve if your model become more complex. But if you look at this mean square error where you have this testing and training, this is different situation where you not only consider the training, but you also consider testing. Actually, this is what people in machine learning would consider like a better way to evaluate your model. That is because if you run your testing most of the time, you will see when your model start to overfitting. And for this case, actually this maybe 2 to 3 parameters is the best, and that's it. But yes, if you have to run your model on validation set, it's taking some time. Unlike these score where you can just run it on training. And if you think about it, for this case, that means once you run the training, then you run the testing. Once you run the training, then you run the testing. That means that the number of runs is like twice compared to these. That's it. So I believe that all of you can answer these quiz, I believe strongly. I think you can do it. I think that's all it is, like an overview of what it's like. But in details, I encourage you to kind of read through it, but don't worry, it's not